Hey, 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 hey. Okay, then just reduce the sound a bit. This should be low enough. I think this is good enough. Well, welcome. This is a educational live stream. It's first of its kind. Already losing my voice. Fabulous. Well, since it's called the education live stream, it's just me showcasing what I do basically in my free time. I'm heavily interested in quantum mechanics, quantum physics, quantum theory. There are different names for the same thing. I thought, why not make a live stream when I'm doing it, so that whenever I feel like I'm bored, what should I listen to, or I want to write notes about something, just go my live stream and do it. So this live stream won't be that long. I think an approximate of 2 hours. I know I have Minecraft in the background, but I don't think I'm gonna be able to play it at the same time that I'm doing this educational live stream. On this live stream I'll be discussing quantum physics. Obviously one live stream is not enough. I'll try to simplify it, go through 1, 2, 3, 4, 5, 6, 7. Technically it's just 6. I'm gonna read the entire thing, and yes, I did read the entire thing. Still more. Obviously I'm reading all this from Wikipedia, and I've chosen those pages because everything in it is actually real and not just like fixed. I don't know, like adjusted or edited, whatever. Just like white space. Okay, didn't know that didn't exist. I have plenty of things to do education live streams about, and let's start it off. Well, I think that's enough introduction. Also, what do you think about the playlist? It's all Kurzgeist, whatever that YouTuber's called. Well, to start off, I would say I highly suggest that you guys watch this video. It's called Quantum Mechanics for Dummies. It's actually not for dummies, just for starters. From London City Girl, 22 minutes. Extremely helpful. I won't play it now, but whenever you'd like to start learning about quantum mechanics, I suggest this video as a starter, and then obviously the channel that all should watch, Exact. I still don't know how to say his name, and also Xurba. Yeah, okay, whatever. It's just these two channels and that video. I would highly recommend that you guys go and watch them. So let's start it off now. Quantum mechanics, also known as quantum physics, quantum theory, wave mechanical model, matrix mechanics. The last two aren't really that famous, including the quantum field theory. And the quantum field theory is on my to read about list because it's extremely interesting. It's in theoretical physics. It's what basically trying to do is just to merge the classical field theory, the special relativity, Einstein's theory, and the quantum mechanics together. I mean, Mixing Einstein's thoughts with quantum mechanics is already hard. Like, so far we can't merge them together. And there's the string theory, which tries to mix them together. And here's the quantum field theory. These are basically theories that are too successful, yet don't work together. No one knows why, and I think that's the beauty of it. Hopefully that you guys know what classical physics is. I think the name says it. There are 4 theories: relativistic mechanics, classical mechanics, both of them are Einstein's. No, actually, I don't think the classical mechanics are Einstein's. Quantum and quantum field. These are basically classical physics theories. So quantum mechanics is basically a subatomic theory. It tries to explain everything that's below the size of an atom. And yeah, subatomic particles. I'm gonna see this graph soon. It started off like in the 17th centuries. People started wondering about atoms and stuff like that. Are they waves? Are they particles? Some scientists won Nobels for proving that it's particles. The others prove that it's a wave. And quantum mechanics basically say that matter is either particle or a radio wave. Not a radio wave, just a wave. With a base frequency, and this frequency is really important, so you can see it in many equations. And it says that quantum mechanics says that the mass is either particles or waves. It can be both, which is quite confusing. An electron is basically a particle and a wave. It depends on how you observe it. Imagine electrons and these subatomic particles like a teenager who's doing whatever they fancy, but when an adult comes and watches them, they act like they are doing their homework. And that's the same with the double slit experiment. Try to draw that. I'm terrible at using the okay, imagine this is the electron shooting gun, and let's do something like blue. This is the okay, that's not very straight. Straight enough. No, this isn't a school channel. I just basically want to explain this, or attempt to explain this. That's the first slit. In fact, that is completely wrong. Or like, this is the first slit. The second slit is like the wall behind. Explain walls, not this video. This is basically the things that our educational system should teach us, but they're basically not doing it. And let's just imagine these. You know what? I'll use dark gray. Let's say these are the electrons. There's a little too much, but you get the point. And let's try and explain it. So this is a electron gun. It shoots electrons. Simple. These are two openings. The blue things are the walls, and when you shoot an electron, this one, when there are observers, the electrons go ahead and hit the wall over here. I'm gonna use green actually. When observers are on, electrons hit these two bases, which basically do make sense in that it's where the gun is pointing at. When there are no observers, let me change the color actually. There are no observers, electrons at the entire thing, and that's quite weird. Is that first of all, is the wave or is the particle? Some people argue that it doesn't really matter on if it's a particle. Maybe it's hitting here and the place where it's meant to hit, and some people say the opposite, which is quite confusing. That's the issue in quantum mechanics, and that's the beauty of quantum mechanics. You can't really agree or disagree to something. It all makes sense and nothing makes sense. And also that's why quantum mechanics says that subatomic particles are both waves and particles. I know they're called subatomic particles, but you get the point. Because sometimes they act like waves, sometimes they act like particles. Sometimes you can measure them as waves, sometimes you observe them as particles. And that is extremely confusing, like no one knows why. And let's go back to here. So the double slit experiment, that's the name of this experiment, and I tried to show you guys this. This is the interference pattern, which is really confusing. Sometimes it does make sense, sometimes it doesn't. Hold on. Can you explain to me the things that you are studying physics because the teacher does not explain? Well, I am not interested in whatever we're studying. Thus, I don't really study. It's just boring. Like, why would you study physics that says things about impulse, momentum? Frick that shit. Let's go start reading a little. In modern physics, the double slit experiment is a demonstration that light and matter can display characteristics of both classically defined waves and particles. It displays the fundamentally probabilistic nature of quantum mechanical phenomena. The experiment was first performed with light by Thomas Young in 1801, but in 1927, Davison and Gamer demonstrated that electron showed the same behavior, which was later extended to atoms and molecules. Light is a wave and made out of photons. Photons are particles, but they are somehow waves. Also, there is another section of quantum mechanics, that's the probability, which is my personal favorite. No one knows why or how that thing exists, the probability. That's why it's my favorite. Like, at least this is an experiment that is doable. Just get an electron beam gun and you can do this experiment, and obviously some observers. And also something I forgot to demonstrate is what, when there are observers, the pattern that electrons shape. So let's just say that this is the wall. And if my drawing was as good as I hope it is. So is that when there are electrons, when there are observers, and you can see that's like this part is this part is that part is in the middle. It's close enough. It's not exact measurements, obviously. So when there are observers, that's the kind of pattern that you see. Like in the opening, in the slit, the electrons are just going to hit. It's only, this was probably a better demonstration than this one. But when we get rid of the observers, it becomes more like So if we join it as a line, you can see that it's kind of like, or if we do it as a normal graph, it would be more like, if you want to be more detailed, it's more like, so the high and low points are where electrons do exist. And this graph basically shows that this is where electrons are. So here's the weird part: when there are no observers, electrons hit things that are even behind the walls, like this area. So on, I'm really terrible at drawing. Hold on. Yeah. So when there are observers, electrons only hit this area. I'm real terrible. Either this area or the area on this side. When there are no observers, they hit the entire thing. Like, what? And that's extremely confusing. I don't think that there are any. Maybe someone drew this thing better than me. Yeah. Hey, okay. So you can see. That's light. We are here speaking about electrons. That's close enough. Yeah, you should probably stop spamming. Like, I'm gonna try to remove all the comments. What? Let's just hide you. Okay, that's a much efficient way of getting rid of your silly dumb things. Here you go. That's not it. Close enough. That's more like try to find the electron one. Hey, yeah, that is awesome. Can I zoom in? Maybe I should decrease the sound a bit. Become more intense. Okay. I'll try to say this graph basically. Close enough. Here's what: if light or electrons, which is basically a particle, let's say it in this way: if photons or electrons or protons or neutrons, all these particles acted like particles, not waves, then in this experiment that's how it's gonna look like. This is the point where they will hit the final wall or sheet or screen. But they acted like waves. Well, it's more spread. It's not equal in one direction or concentrated in one place. Yeah, that's close enough. But I actually don't have time to read this, so I'll go to your cat soon. Yeah, also this equation is quite important. It is the energy element and frequency of it with blanks constant. I'm gonna do a separate live stream for blank if I ever became interested at it. I'm slightly interested, but not that interested compared to quantum mechanics. I don't want to get into the maths part, seriously. I will do a full live stream about Planck. He is considered as the father of the quantum theory. He's a dope one. Let's try this unsolved problem in physics. And the corresponding limit of quantum mechanics is there a preferred interpretation of quantum mechanics, quantum description of reality, which includes elements such as superposition, wave function collapse, give rise to the reality observed. I want to explain superposition, but it's very confusing. And it's not something that I can easily explain. I mean, I'm doing a terrible job at explaining quantum mechanics already. Yeah, I did explain one experiment. I'm gonna get rid of it. Here's what. In physics, there are 17, if not, yeah, there are 17 particles that are below the size of a proton. And they are categorized into 3 main categories: quarks, leptons, and bosons. Bosons are into 2 different types of particles. Bosons are the force carriers, or the things that you interact with, and other things are basically matter itself. There are particles that carry force and interaction. There are other particles that carry matter and waves, basically. There are 6 types of quarks. You have the up, down, charm, strange, top, bottom, and these are what make protons and neutrons. This is what holds them together. And then there are leptons, as the electron and his cousin, the muon. And this one that I can't really explain, I don't understand, the tau. That's the issue with quantum mechanics. Once you start learning something, basically have a huge list of to learn, and you just keep on adding things and adding things and adding things. Bosons, 5 bosons, 2 different categories: vector bosons and scalar bosons. Vector because they have a direction, and scalar because they don't have a direction. There's only one scalar boson, which is the Higgs. My personal favorite, because it's the H letter. It's also the reason why I love hydrogen so much. Get away from that, we have gluon, photons, Z bosons and W bosons. I don't know anything about these. I mean, in total, I think I know 1, 2, 3, 4, 5, 6, 7 out of the 17. That's a bit terrible. I don't know if I should include these 2 or not. However, Higgs basically about gravity. Photon is light, and it's the fastest thing. There is another one that is, I think, faster than photons, which basically is against what Einstein said, that there's nothing faster than light. I personally stand with quantum mechanics at this point. I think there are definitely things faster than light. I mean, why light is the fastest? It's made out of a particle, but nothing special about it. I mean, its characteristics, you can find it in other particles as well. what was the thing I'm gonna talk about? Yeah, okay, so neurons are made out, neutrons made of 2 down quarks and 1 up. And if you're wondering why is that, well, just look at the chart. You can see that a down quark has a minus third charge, and an up has 2/3. We have 2 downs and 1 up. They cancel out each other, have a neutral neutron. And XP for some reason woke up. Not their time. Okay. Protons have 2 up and 1 down. With 2 ups you have 4/3 of a charge, but with 1 down it cancels that extra third and becomes a +1 particle. Electrons are basically a quark. I mean, it's a particle similar to quarks. The only difference is that it's not made out of thirds. It's straight up -1. Notice these are basically all minus and all positive, all minus. You can, if you combine 2 strange quarks with 1 charm quark, you can make a something similar to proton or neutron, so on and so forth. Once we reach that point, once we become able to create particles, I think that will be the peak of humanity. If you are already able to make smallest things in the universe. And also some people argue that maybe there is something smaller than these. That is possible, but we are not yet able to explain atoms and their functionalities, how they function and why they function. And I don't think that we are ready to go even smaller than this limit. If Planck's length, which is the smallest length, is truly the smallest length possible, these are far bigger than a Planck's length. In fact, why not try Google how long is a photon? One-tenth of a nanometer is good. Nanometer to Planck's without this. So here's what: if a photon, let's say 1/10 of a nanometer. Where is the page? Yeah. So if a photon is 6.25 times 10 to the power 24 of a Planck's length, there's a huge gap. I mean, I'll try to demonstrate it. How can I get rid of everything? Yeah, that will take so long. An eraser. Probably more efficient ways, but whatever. Let's go back here. So we said this is Planck's. Hold on. Say this Planck's length. A photon will basically be. Hold on. Go back. Photon will basically be. I'm not going crazy, I'm just trying to demonstrate it. And more. We said this is Planck's length. A photon will still be more than that. So what lies between this space? This extreme space? from this length up until a photon. I should just try to demonstrate it with points. So here's blank's length. Here's a photon. Just extremely small. Let's try blue. There is that's a terrible straight line. Since that this is blank's length, and let's just say that it is the smallest thing. There's nothing behind it. That is as small as it gets. That's a terrible circle. And let's say this is a photo. There is this huge, extremely huge space in which maybe there are particles that exist within it. I mean, this space is basically only this space in comparison to size of a atom. Let's try Google this size, length of an atom. An atom can be as small as 0.1 meters, though it can be bigger. Okay, that's an actually interesting question. Oh, so they do have a life point. Yeah, atoms are extremely small. So this entire length can be the length of an atom. What lies between here is basically protons and all particles, neutrons, electrons, Higgs, ups, downs, strange, charm. There are no left or right, so that's sad. I honestly think that between a photon and blank's length there is a other particles. That's too much. Higgs length. One-hundredth the size of a I mean, there's obviously no actual thing of what is the size of a Higgs or a particle, since we don't have enough technology to measure it. Obviously that's a 100th the size of a proton length. Yeah. Here you go. And that's extremely small. That's already smaller than what you might think of it as. 1 Also, protons are far smaller than photons. Really sorry then. I seriously thought that photons are smaller than protons, because that does make sense. So in fact, this should be a proton, not a photon. Photons don't have a charge. Yeah, let's get rid of this entire thing. Let's keep going with all the things that I'm trying to cover. In one live stream, I'll most likely fail. So here's what: proton length to blank length. Come on, give us like the SI unit. No, not in meters. Okay, minus 35. Let's just end it with extremely small. That's none of our interest now. Yeah, I lost what I was gonna say. I forgot. I'm gonna touch antimatter now. Talk about it later. I want to discuss Bell's theorem. I only heard it like a week ago and I didn't read anything. I know it's an inequality theorem. It's quite crazy, to be honest. That deserves a live stream by itself. Let's go into the overview. It states that any physical theory that incorporates local realism cannot reproduce all the predictions of quantum mechanical theory. For hidden variable theory, if Bell's conditions are correct, the results that agree with quantum mechanical theory appear to indicate superluminal, faster than light effects, and contradiction, I can't even say the word, to the principle of locality. The theorem is usually proved by exploration of quantum system of two tangled qubits. Qubits are basically a unit. As stated above, the non-photon. Most common examples concern spin or polarization. Quantum mechanics allows predictions of correlation that would be observed if these two particles have their spin or polarization measured in different directions. Bell showed that if a local hidden variable theory holds, then these correlations have to satisfy certain constraints called Bell's inequalities. Well, look at it. I know there is an experiment for this. What? Name this. They got superposition. I feel like that's too much. Not really sure about that. Let's go for super luminal, or faster than light. So it basically says that there are things that are faster than light. Einstein basically responds with impossible. There is nothing faster than light. Here's one. In physics, the speed of light in a vacuum is assumed to be a constant. However, hypothesis exists that the speed of light is a variable, so sometimes faster, sometimes slower. Speed of light is a dimensional quantity, so cannot be measured. Measurable quantities in physics are without exception dimensionless. They are often constructed as related dimensional quantities. For example, when the height is measured, its height dynamic per meter stick. Yeah. The units are defined to be independent and so cannot be described in terms of each other. As an alternative to using a particular system of units, one can reduce all measurements to dimensionless quantities expressed in terms of ratios between the quantities being measured and various fundamental constants as Newton's constant, speed of light, Planck's constant. Physics can define at least a 6-dimensional constant be expressed in terms of the social ratios, the independent of one another boundary thing. Okay, so I confirm I'm looking for. Oh, I actually read. Wait. Oh wow. I read the variable speed of light. I didn't read the general relativity. Should have looked at the title first. Okay, let's forget what happened the past 5 minutes or so. Was developed after. So general relativity was developed after special relativity to include concepts like gravity. It is the principle that no object. That's the important part. No object can accelerate to the speed of light in the reference frame of any coincident observer. In other words, nothing can go faster than light. Nothing can reach the speed of light. My nose is blocked for some reason. It permits distortions in space-time fabric that allows an object to move faster than light from the point of view of a distant observer. One such distortion is an uncovered drive, which can be thought as double space-time and carry object along with it. Another possible system is the wormhole, which connects two distant locations as though by a shortcut. Both distortions would need to create a very strong curvature in a highly localized region of space-time, and their gravity fields would be immense. To counteract the unstable nature and prevent the distortions from collapsing under their own weight, one would need to introduce hypothetical exotic matter or negative energy, in other words, anti-matter. So it is possible that wormholes exist. Einstein did say that they exist the same way that he said that black holes do exist. Black holes were proven that they do indeed exist. It's just that it's time for wormholes. But honestly, I'm really waiting for the discovering of wormholes. I mean, that would be amazing. We'd be able to travel faster than light. Imagine if you go inside of a wormhole, you somehow don't die, since it seems like the risk is far less than a black hole. And let's just not talk about white holes. That's another interesting thing. So if you can go through a wormhole, you can experience time distortion, and once you come out from the other end, you might have advanced 1 second to the future, or a quadrillion seconds, minutes or hours or days or years or light years into the future or the past. Well, we won't be able to know how fast did we go or how far we went. I mean, if we were able to create wormholes, I mean, that would be fabulous. Imagine creating a wormhole that allows you to go 10,000 years into the future or 10,000 years into the past. Maybe someone else will create a wormhole for a year in the past. Maybe a new shop called Reverse Your Mistakes, in which you go through a wormhole, you go back an hour ago, and you experience the same thing you've done horribly wrong, and you try to fix it. That would be quite amazing. That's just probably not an actual application for a wormhole. We'll see about that. So far they are not proven to be there in the universe. There is a possibility, but who knows. There are some quantum truths about the universe, which are arguably the weirdest things we've discovered about the universe. Well, first thing is, everything is quantum. It's not like some things are quantum mechanical and others are not. Everything obeys the same laws of quantum mechanics. It's just that quantum effects of large objects are very hard to notice. This is why quantum mechanics was a latecomer to the development of theoretical physics. It only showed up like few centuries ago, I think 2 centuries ago, between physics a few thousands of years ago. This wasn't until physicists had to explain why electrons sit on shells around the atomic nucleus that quantum mechanics became necessary to make accurate predictions. Well, it's a bit of a mistake. They made quantum mechanics to make accurate predictions, and now there is an infinite, not an infinite, it's a nearly infinite amount of probabilities. I mean, there is a probability that the light that your body emits, yes, a human's body does emit light, reaches the end of the universe and then comes back to you, there is a probability. How likely? 1 over nearly infinite percentage. It's extremely unlikely that such a thing happens, but it is possible. And that just increased the amount of predictions that can be made. And that's just unfortunate for all the physicists that worked on it. And also, quantization doesn't necessarily imply discreteness. Quanta are basically discrete chunks by definition, but not everything becomes chunky or indivisible in short scales. Electromagnetic waves are made of quanta called photons. So the waves that can be thought of as being discretized, electron shells around the atomic nucleus can only have certain discrete radii, but other particle properties don't become discrete even in quantum theory. The position of electrons in the conducting band of a metal, for example, is not discrete. The electron can occupy any continuous location within the band. We're a bit going to superposition in this statement. The energy values of the photons that make up electromagnetic waves are not discrete either. For this reason, quantifying gravity, should we finally succeed, as doesn't necessarily mean that space and time have to be made discrete, but on the other hand, they might be. Gravity and light, they might travel at the same time, maybe depend on each other, or they're just basically different speeds. What if space-time is faster than light? I mean, it's a bit weird when you think about it. I mean, it's possible for light to go faster than its current limit. Can it go slower than its current limit? I mean, why does light move this fast in a vacuum? I mean, it should require an extreme amount of energy to reach that speed, but somehow photons don't have that much energy. I mean, the light that your phone or laptop or screen, the light that comes from that screen which watching this live stream, you're not really using like an amazing amount of energy. By amazing, I mean like energy that has never been created since we were able to create energy. Just photons don't have that much energy, but they are the fastest in the universe. What if we added energy to them? Does that increase their speed? What would be weirder, more weird, is if we add energy to photons and they become slower. That would be just effed up, straight up, honestly. Also, I need to clarify that quantum entanglement is not the same as superposition. A quantum superposition is the ability of a system to be two different states at the same time, and yet when measured, one always finds a particular state, never a superposition. Let's try to demonstrate that. Yeah, what you see in front of you is a electron. Let's just say that you are unable to see it. Okay? Where is that electron? What current state is that electron? It might be a wave. It might be a particle. But you are not observing it at the moment. You don't know for sure. Where is that electron or whatever? You still don't quite know. That's because you're not observing it. Now the electron is in something called superposition. It exists everywhere, anywhere, at the same time. But once you observe it, well, once you observe it, that's all what you see. Just an electron. Or maybe that's how you observe it. Or maybe this is where you observe it. This is where you observe it. Or here, or here, or there, or there. You don't know for sure where it is if you can't see it. Can't observe it. Once you start observing it, it takes place. It takes place in one of its possible places to exist in. Which leads us to Schrodinger's cat experiment. A cat, a flask of poison, and a radioactive source. Here's one. Is a thought experiment, sometimes described as a paradox, devised by the Australian physicist Erwin Schrödinger. It's quite hard to say his name. In 1935, to say that when he saw as the problem of whatever that is, and want to add to my to learn list of quantum mechanics applied to everyday object. Sanu presents a hypothetical cat that may be simultaneously alive and dead at the same time, a state known as a quantum superposition, as a result of being linked to a random subatomic event that may or may not occur. The experiment is also often featured as in theoretical discussions of interpretations of quantum mechanics. Schrödinger coined the term entanglement in the course of developing the thought experiment. Here's the cat, this is the poison, that's hammer, and that's the radioactive source. Placed in a sealed box, you can't see. An internal monitor detects radioactivity, a single atom decaying. The flask is shattered, releasing the poison which kills the cat. The Copenhagen interpretation of quantum mechanics implies that after a while, the cat is simultaneously alive and dead. Yet, when one looks in the box, one sees the cat either alive or dead, not both alive and dead. This poses the question of when exactly quantum superposition ends and reality collapses into one possibility or the other. So let's try draw that or a similar experiment. Is what? Let's say that this is kind of a box. I haven't finished. But that's just a terrible looking box. It's good enough. I'll end it here. Okay. Let's say that there is a toy within it. Now when you observe it, you can see that the toy is there, and the fact that is true because you can observe it. If you do, okay, that didn't work out as the way I meant for it to work. If you observe it, yeah, that's better. If you can't see it, is the toy there or not? Is the toy there or not? Is it still purple or did it change color? Well, you can't really see it until you can observe it. Same with the cat. If a cat is there and you shoot radioactive particles at it, and theoretically it should be dead. Now at this point it's either dead or alive, not both. If you observe it, it's dead. It's alive. I think that's a good enough explanation. That's basically the experiment. I'm terrible at drawing, so I won't really blame you if you don't understand. Position of relatively large. Let's watch this video. Yeah, that's observing. The quantum object is basically the cat. Imagine. Yeah, that's the kind of the wave graph that you see. Well, I think this is a good enough video. Well, in this case, it showcased an atom, I showcased the toy, the experiment showcased a cat. The video went a little too deep about the time it takes for something to take a state, size of the atom, if it's excited or not excited. That was good enough. I'm not gonna do the equation now, do it later on, but here's what. it's really hard to stop this. No, I didn't. Okay, it's just too low. This will be the end of the live stream. Also, I got been streaming for an hour. That's kind of like a mini lecture. These are the 17 particles that make up physics, that make up the life. Basically, you as a human are made out of cells. Cells are made out of organelles. These made out of atoms. Atoms are made out of protons, neutrons, or electrons. Protons are made of 2 ups, 1 down quarks. Neutrons are made of 2 downs and 1 up quark. An electron is a particle itself. It lies within the leptons category. And also, we've discussed a little bit about light and gravity, space-time fabric, and the speeds of them, and the fact that it's not a fact, it's just there's probably something faster than light. That there's no obvious reason why photons move at this constant speed. And is it really constant? In vacuum, slightly. Sometimes it increases or decreases, but scientists blame the devices they are using, as they are not good enough to show you the exact values, and they argue that if we had a perfect machine to calculate the speed of photons, we would get the same number always, which is basically a constant. And now it really depends on what you think of it. I personally think that photons aren't the fastest, or maybe there are different types of photons that, well, are either faster or slower than it. Or maybe there's another particle that's faster than it. Maybe Higgs, which is related to the gravity, moves faster than a photon. But gluons are the same as photons in terms of mass, charge, and spin. Why aren't gluons? I can't really Google it. Gluon. Why aren't they faster than photons? Why are gluons what attaches the up and down quarks together in a proton or a neutron? I mean, they're called gluons, similar to the word glue. Okay, well, gluon is basically another discussion to have, which is not the point now. Soon, probably. It's basically gluons hold up and down quarks to create neutrons or protons. Even though it's kind of weird that different charges connect, but it's called the weak force. It's not really weak, it's just because it's too small in size. It's called weak force. And also the universe is made out of 4 forces: gravitational force, electromagnetic force, the weak nuclear force, and the strong nuclear force. We don't know for sure if there's another force that rules the universe. These are basically the 4 rules of the universe, and those 17 particles are the 17 figures in the game that is called the universe. And on this note, I'll end this live stream, first of its kind. I think that I did an okay job of explaining what I came here to explain. Let me just increase the size, you can see it. And I hope that soon enough we'll be able to control particles, so I can go inside Microsoft's servers and consider my Windows as an activated Windows. since I have some reason I bought an activation key, but somehow it don't lasted for a year. That's just weird, to be honest. I mean, now it doesn't display for me, your Windows key is about to expire. It just shows, go to settings to activate Windows. And that's something I'm okay with. So, what are my predictions? I think that within the next 50 years, we will know 1,000 times more things about what makes the universe than we currently know. If you look at the 20th century, at the beginning of it, the first 20-30 years, we didn't know much, but at the end we made so many crazy things that we still use, such as the internet, airplanes, cars. Even though they existed before, it's just that they improved so much. I mean, now your phone has a better computing power than the power NASA had when it sent the Apollo 11 mission to the moon. I'm not going into the no one landed on the moon or whatever. That's just something ridiculous. I think people did land on the moon. Why aren't they doing it again? I'm not sure. I seriously don't work there. Maybe I'm gonna work there, who knows. But for now I'm just a small YouTuber, a 15-year-old student who hates what he's learning about in school. He just educates himself using the lovely thing created by humans, the internet, in the late 20th century. We're only in 2019. I think by the next 11 years we will still just be in the process of discovering new things, and later on we'll be able to apply these. I mean, quantum computers are already a in progress thing, and then there are people like you two in my comment section. Yeah, you guys are just dumb. Also, I don't think that we're gonna land on Mars within 2024. I think in 2040s. Yeah. Hopefully by that time I'll be able to get myself a ticket to Mars. Who knows? I might be the first human to die on Mars. Or I'll just go to Mars and set as many world records, or in this case, universe records, as possible. It's crazy. These are the type of things that if you start thinking about them late at night, you will never sleep. Just keep thinking of them for the next few hours, and then realize school is after 3 hours, and it's too late to sleep. So you go to school like you're drunk or something. But again, as I said earlier on, which was about 10 minutes ago, thank you guys so much for watching. If you enjoyed, make sure to hit that like button. It's my first educational live stream. I'm just learning. I'm in the learning process of how to make an educational live stream. More to come if I ever have time. For now, read more. Read books or read from the internet. And don't stress yourself about what you're learning in school. See you the next time. Stay awesome. And you two are banned.